Okay, everyone, welcome. I'm Lorenzin, who's going to tell us about the Aldous-Hoover theorem and categorical probabilities.
Okay, well, thanks to the organizers and also to everyone here. This paper that we are working on right now is joint work with Leihao Chen, Tobias Fritz, Tomáš Gonda, and Andreas Klingler. So to talk here about the Aldous-Hoover theorem and categorical probability, we will divide the presentation in three. First, a rough idea of the statement. Secondly, the categorical probability framework, so Markov categories, and then we will talk about the Aldous-Hoover theorem in this synthetic perspective. So for the rough idea, I will start off with the definitive theorem, which is an easier statement. And the idea is as follows. We have Cooper, the guy in the green t-shirt, who decides to play individual games with his friends. And he wins, he loses, whatever. But keep in mind that we need to assume something very important for math, which is this is an infinite sequence. So Cooper has a lot of friends. And yeah, also, let me tell you that we are not really interested in the outcomes per se, but we are interested in the probabilities of victories of all games. Okay. And now we ask that Cooper is a strong player, psychologically, in the sense that if we start to move around a finite number of his friends, is gonna still perform in the same way. And with these assumptions, the definitive theorem tells us that if we do not know the outcome of the first two games, and but we do know the rest of them, then we can do independent predictions on the first two games. And this is the idea of the definitive theorem. For the Aldous-Hoover theorem, Cooper has other friends with him. And so we have like these two groups. We have an infinite number of Americans, an infinite number of Europeans, and they all play games with each other. And yeah, so I put A for when the American win and E for when the European win, just for our sake. But of course, we are still interested in the probabilities of victories of each single game. Okay. As before, we want this invariance. Okay, so for if we move around a finite number of Americans or we move around a finite number of Europeans, then the outcome does not change. And now the Aldous-Hoover theorem tells us that if we know the result of all games but the first four, then we can do independent predictions as before. But there's something more, which is like that every of these four games, okay, they only depend on their row, their column, and the tail. So, well, the row is telling us the skill of the American, the column is telling us the skill of the European involved, okay, while the tail is telling us the general difference in skills. So to say, like, if we are playing Texas Hold'em, maybe the Americans are better. If we are playing football, maybe Europeans are better. So that's the idea of the general differences. Okay. I hope now you have a little bit of an idea of what this theorem is about, and we can go on with Markov categories. If you have any questions about the statement, feel free. Okay. Yeah.
Was the fact that it was the first two, like 2 by 2, was 2 important, or could that have been any finite number?
Yeah, any finite number. Yeah. It's just for my own sake. I didn't want to get involved in the package too much, but yeah, any finite number works for both the definitive theorem and the Aldous-Hoover theorem. Okay. So what are Markov categories? Well, Markov categories are symmetric monoidal categories. So we have a tensor product and a monoidal unit, which we also require to be terminal. And then we also have this additional structure, which is this copy map and the deletion map. well, actually the deletion map is not really an additional structure. So we have the copy and the deletion. As you see, the copy goes from X to X tensor with itself, and the deletion map goes from X to I. And since I is terminal, this is the only map that we have of this form. Okay. For a Markov category, one needs to require that these two maps will give you a commonoid structure on each object, and also there is like this structure has to be well behaved with respect to the tensor product, but I don't want to delve into the details. The only thing that we care about for us is that the copy is an idea to copy information without introducing randomness. Okay, so this is going to be like a deterministic way of having the information twice. Okay, this is very important in probability in the sense that when you have a probability, you want maybe you want one which is identically distributed and with the same information, and this is how you get it using the copy. Also, another thing is that for us, we are just gonna talk about probabilities, which are morphisms from the monoidal units. Everything seems to be like we should be able to generalize it to also other morphisms, but for the sake of this presentation, we'll just see probabilities. Okay, and now maybe I will tell you about a toy example that allows us to understand what is the concept of Markov categories and why these things are called probabilities. So if we consider finite sets, what can probabilistic morphisms be? Well, we do know functions, so we take an element in the domain and we connect it, associated to it, an element in the codomain. But if we want to consider something with some randomness, well, we want to associate to an element in the domain something in the codomain with a certain probability. And this is the idea of Markov kernels. So like for this first element, we go here 50% of the time, and here 50% of the time, so on and so forth. We can have the same tensor product that you may imagine for finite sets, i.e. Cartesian product, and everything works out fine, composition, and the tensor product is okay? And this will give you a Markov category. So we're very happy, but the definitive theorem already is talking about infinite arrays. So finite sets are not as good as one might think, and that's the reason why we use standard Borel spaces, which we already saw a little bit. So we are interested in standard Borel spaces with Markov kernels. I don't really want to give you details of Markov kernels for measurable spaces, because but the idea is basically the same that we saw for finite sets. And standard Borel spaces, what are those? Well, you can use this theorem, which is the Kuratowski's theorem. Any standard Borel space is isomorphic as a measurable space to either R with the Borel sets, Z with the power set, or a finite set with power sets. Okay. And this is this will be our framework for many reasons, which I will explain or also not. Just a good amount to say. And this is maybe the most important definition, I guess, that I will give. So if we fix a probability from I, so it is a morphism from I to X, W, and Y, then we say that X is conditional independent of Y given W, and we will write this in symbols, but not really too much. If we have this string diagram, okay, this equality of string diagrams, what does this string equality means? Well, actually, you just need to see like the inputs of F and G, okay? Like the input of F is only W, but there is no Y involved in the input of F. So this means that X is not concerned with what happens with Y. And the same is true also for Y, like we have no connection with X. And that's the reason why we call it conditionally independent. Okay, for some F and G. But now if we actually require F to be equal to G, which is gonna be our cases generally, then we can say that X and Y are identically distributed given W. And some of you may argue that if F is equal to G, then X is equal to Y, right? But generally we want to label objects with different namings because, well, if I say X is conditionally independent of X given W, you don't even know what I mean maybe. But if we say X1 is conditionally independent of X2 given W, then this makes sense. So this is actually what we're going to do. We are going to have an object an infinite amount of time, and we were going to label it with a natural number or a couple of natural numbers, as in the case for the Aldous-Hoover theorem. This thing can also be generalized for a finite or infinite amount of xi's appearing instead of just X and Y. And so we can also use this new symbol, which is a little bit more general. Okay. And this concludes the second part. So if you have any questions now. Okay. For the Aldous-Hoover theorem, we will do exactly as we did at the beginning. Okay. So we first talk about the definitive theorem. And to talk about the definitive theorem and also the Aldous-Hoover theorem, we need the tensor product of this infinite array and the infinite matrix. And to do so, we just introduce the notation xn, okay? And basically, this is given by a limit procedure because we have this deletion. So if we consider like a finite set, okay, we can consider a finite tensor product associated to it, and then using the deletion on one of the components or more of these components, you can get this diagram, this morphisms, and now you just take the limit of this procedure, and you get the countable tensor product. I'm putting something under the carpet, but we don't care. And of course, with this idea in mind, I think you can imagine that if I take a finite permutation, sigma, I can use the swap a bunch of times, and then I will get this automorphism x sigma. And now an exchangeable probability will be a probability which is invariant of every finite permutation, which is exactly what we required at the beginning, right? We can move around a finite amount of players. And so the definitive theorem tells us that for every natural number n, we have that the first n entries are going to be conditionally independent of each other given the tail. Okay? But what is more actually is that they are identically distributed given the tail. So these maps are actually the same. Okay, and as I said before, we are labeling these objects, although they are still the same object every time. Okay. About the assumptions, the synthetic proof of the definitive theorem holds under the following assumptions. The first one is, well, we want to state the theorem, so we need countable tensor products. Secondly, we want conditionals, basically because we are doing probability, so it's good if we have conditionals. And these assumptions were also used in the previous paper by Tobias Fritz, Tomáš Gonda, and Paulo Perrona. where they use these two assumptions and another one, which is more about the monadic nature of the Markov category involved. But here we do not want to go in that direction, and we actually use a new information flow axiom, which is called the Cauchy-Schwarz axiom. I'm gonna talk about this axiom a little bit more after. But for the moment, I want to tell you and to stress that Borel-Stock satisfies these assumptions. So we are very happy. And also these assumptions do make sense. But more importantly so, is that under the same hypothesis, we can prove the Aldous-Hoover theorem. So these are our assumptions. And if we were to use the monadic nature that was studied in the previous paper, then we wouldn't have enough to prove the Aldous-Hoover theorem. So this is very important that we have this new information flow axiom. And it is for this reason that I wanted to just let you see the statement of this axiom, just for people who are interested in this. For us, it's just that, well, we have a way to control this equality. And this equality is very important because for Markov categories, the last equation, this equation, is actually telling us that F is P almost surely equal to G. So basically, this axiom is a way to control almost sure equality. And that's how it's used basically in our proof. Another very important thing is that when we try to state the definitive theorem, we have only one thing going on basically. So we can state it using string diagrams in an easy way, but this is not the case for the Aldous-Hoover theorem because it's painful to write. And so we need to use this plate notation, and you will see why it will be painful to write in a second. Yeah, so we need this plate notation to just write a bunch of copies of the same morphisms. Okay, so the definitive theorem, for instance, will have this form, which is a little bit nicer if you want, but also not really interesting for the definitive theorem. But you will see for the Aldous-Hoover theorem. Okay, so as we said at the beginning, when we are considering the Aldous-Hoover theorem, we want this row and column exchangeability. So if we have a finite permutation and we use it to permute the rows or the columns, this is not going to change our probability. And this is exactly what we require. And okay, so this is the statement. Please don't be scared too much. Okay. So we have our probability, okay, and this is gonna be this decomposed in this way. We have the tail, okay, so we have this part which is greater than n and greater than n, okay, and this is the general difference in scale, okay. Then we have the columns and the rows, okay, the scale of the American and the European involved, and we have the outcome of their match. And basically here we will have a copy of G for every column, a copy of F for every row, and then we have a copy of H for every entry. So as you can imagine, if we try to write this string diagram without this plate notation, it's gonna be very messy very soon. So yeah, this is actually the idea, and here I'm using like this double wire to tell you that here we only have rows, and then we go back to columns. Here the same, and here we had only one entry, okay, associated to I and J, and then we have then we put on we go out of the column box. And that's the reason why we have a double wire and then a triple wire to say that we are at this level. So something about the idea of the proof graphically. So the gray area means that we are conditioning over that, okay? As we said at the beginning, remember the conditional independent given W. So the gray area is W here, okay? And now we need to prove that all of these entries are independent of each other. And this is the first part. And then we have the second part, which is we just marginalize everything in the n times n matrix, but one entry. And then we show that this is independent of all other rows and all other columns, given its row, its column. Well, I'm not that good. Okay, and also the tail. Okay, these two parts only require you to use the definitive theorem and some properties which are very well known to people who do probability theory, which are the semi-graphoid properties. But the third one is where we need to use the Cauchy-Schwarz axiom. So here we marginalize the whole n times n matrix, and we need to show that all rows and all columns are conditionally independent given the tail. And with all rows and columns are conditionally independent, I mean every row is conditionally independent of every other row and every column. Okay, and of course vice versa. With these three are basically three lemmas that we prove, and then putting them together, we end up with the Aldous-Hoover statement. And there is actually another way that we are working on right now, using the diseparation criterion and so other order properties about the DAG structure that is under the Aldous-Hoover theorem. And okay, thank you for your attention.
Questions?
Yeah. So at the end in the, just go back to the,
Take one.
is the 2 here significant? As in the 2 dimensions? Like it only goes up to matrices, or could you have done this for 3-dimensional arrays?
Yeah. We're trying to do something more general. At the moment, this is what we're working on, but yeah, I think we can find a way to state and prove something way more general than this. Yeah.
You used plate notation. I've seen plate notation before, and I'm just wondering, do you know of, like, have you formalized plate notation at all? This is a bit of a holy grail for a friend of yours.
So that part, Andreas is working on it.
Oh, okay.
And I'm letting Andreas do that. But yeah, I think that the only problem with that, okay, so this definition is okay. The real problem is trying to make this understandable, okay?
Yeah.
Because that's gonna be a hard task. And yeah.
So you're saying the hard part is compositionality?
Yes, yes, because this compositionality is like on the side, right? So you cannot even close the box. You need to act inside the box. That's a little bit painful.
The past problems, like thing I have seen plate notation for basic networks.
Uh-huh.
I know that they can be translated into this tree diagram. I don't know how, but I was wondering if this is kind of the first time plate notation is used this way, or I mean, you're saying you're working on it. Or if it has been used with fact.
I think we're the first ones, and actually maybe Dario knows something more than us because he's the one who suggested us the plate notation.
I've used it a bit, and like you can formalize it with kind of, you can have the type of plate for each functor, I guess, but I don't have this overlap, like this overlap is much more complicated than what I considered. I would love to see how it's really.
Evan Patterson used it informally like this. I don't know if he had a nesting, I don't know if he had overlap, I think he had nesting. But not overlapping boxes, in his dissertation.
I don't wanna like harp on the statement. Something is an easy way to convince myself that a picture denotes something well defined. If I know easy way, that's okay.
That's why we call it a holy grail.
If you want, I can scare you and let you see the statement for n equal to without the plain notation.
Okay, I would like to be scared.
Okay. Are you happy?
Scared.
Got the color.
Yeah. Color to 8 readers high. I mean, that's just a mess. Yeah.
That answers my question.
Yeah, so I mean, it's this functorial function, like saying J less than N would be after that it tensors something with itself in times. You're applying, the box is. Functorial box is like nowadays.
There are also things sticking below and above the box, which would be copy in this case. For example, you can have a multiset box that I've used this where you use the accumulate like multinomial distribution. So then you have copying on the inside and accumulation on the outside. What's really unclear is what happens on the sides of the boxes.
Yeah.
Why is it called choice?
Yeah, right. Good question. I hope there's someone asked that. So we can use an inner product interpretation. We omit the P under it, and now we can write the antecedent as F, G, and GG. Okay, good game. And this implies that F is equal to G, right? Now, the idea is that if we were able to do some algebraic manipulation here, we could write this thing as Fg squared equal to the inner product of F with itself and the inner product of G with itself. And if you use the Cauchy-Schwarz inequality statement for the equality, you get that this is exactly the implication that you generally have. So it is a Cauchy-Schwarz equality axiom. Is that good enough? Okay.
Similar question, why should I think it's axioms? So what's the equation like that? So is it somehow, is there some easy reason why this is called a standard cross basis?
Yes. So basically, when you try to prove this, you are asking if I have that F minus G is, squared is equal to 0 almost surely. Can I say that F is equal to G almost surely? And this is basically like a positive definite kind of thing.
Why F minus G squared 0 corresponds to what?
Yeah. But maybe you're better than me at this. Where is? Oh. So. Huh? Oh. Okay. Can I use this? Maybe it's better. I don't know. Well, I'm not really sure exactly how to write this, but it should be like f. Yeah, there is like the integral of f squared. Then you have that this is equal to the integral of f times g, and this is equal to the integral of g squared. And that's basically the reason why at the end of the day you get that you get the integral of f squared minus fg, which is equal to 0. And now if you look also on this equality, you have the integral of fg minus g squared, maybe on the so the integral of minus fg plus g squared, and this is equal to 0. Now you add these two up, and you get exactly f squared minus 2 fg plus g squared, and this is exactly the integral of f minus g.
Yeah, and I think he's writing maybe on the screen right now or something.
Thank you.